Hello, thank you. And thank you especially for the promotion to professor. I am sadly only a doctor, but yes, I'm nevertheless very happy to be here this evening. As Hassan said, I'm Dr. Katy Clough. So I am an Ernest Rutherford Fellow at Queen Mary University of London, which is just down the road. And this evening I'm going to be telling you about the limits of astrophysics. That's what I promised to tell you. So the title, At the Limits of Astrophysics, so that's the title of my talk, but it's also a bit of a description of me and my research. So you'll notice from my slide that I'm actually from the maths department at Queen Mary University. We've got some mathematicians in the audience. And so actually all the mathematicians think I'm an astrophysicist. But all the people in the astronomy unit who are real astrophysicists think I'm a mathematician. But I actually sit in this very interesting and rich space that exists somewhere between the two things. So especially for Einstein's theory of general relativity for gravity that I'm going to tell you a bit about this evening, it's somewhat of a mathematical theory, and yet it has consequences in our universe. So it sits somewhere between the two things. So as Hassan was saying, this is actually the first in a series of talks that are going to be given by Queen Mary researchers. And when I got the list of all of everyone else's abstracts and titles, I thought, wow, this is really amazing. So there's things like supernovae, exoplanets, beginning of the universe, dark energy, dark matter, all this kind of stuff. And I thought, that sounds really impressive. It actually sounds like science fiction. And I thought, if I wasn't working in this field, I might find it really difficult to know where the line is between science and science fiction. If I can have, all of these crazy supernovae and exoplanets and stuff like that, why can't I have wormholes and warp drives and things like that? And so I thought it would be fun this evening to try and explore with you where that boundary lies, which is also, as I say, kind of related to this space that I exist in for my research, somewhere between mathematics and astrophysics. Okay, so let's get started. So an alternative title for my talk is, what's the difference between a crazy idea and a brilliant one? So it turns out, of course, if you know anything about the history of science, that we're not very good at telling the difference between these two things. So often we've thought that things were very good ideas and they turn out to be completely wrong, and vice versa. Things that we thought couldn't be true actually turn out to be reality, the reality of the universe that we live in. And so I'm going to focus on three crazy ideas for this evening, and I've sort of ranked them in order of craziness. So actually for the second and the third one, it's a bit of a matter of taste. Like, it depends, how you feel about these things, and it depends on the specific type of wormhole or warp drive that you want to have. But definitely the first one, black holes do exist. So black holes are really good science and not science fiction, which is surprising because they do, as I say, on the face of it, sound kind of completely mad. So before I tell you about these three types of objects, I have to tell you a bit about this really crazy but super brilliant idea, which is space-time curvature. So I think, for me, this is one of the most brilliant but also most crazy ideas in the history of physics. This is one of the things where when you first encounter it, you just can't accept it. Like, deep in you, you're like, no, that's not how the universe is. But it is, right? It's just that you don't have the right intuition because you were born and lived most of your life all of your life, hopefully on Earth. And you've never flown to a black hole or traveled at the speed of light. You've, as far as I know, you've all been here for your lives. So you just don't have the right intuition for these very strong gravity environments that you have, for example, around black holes. So at the core of this idea is this idea of space-time curvature. So let me break it down for you a bit. So the first part is space-time. So this idea of space-time is that somehow space and time are not separate things. They're not independent. They somehow depend on each other. So they're part of this bigger thing called space-time. So in this picture, this is probably how we would think about space and time. So along the bottom, there's space, and going upwards, that's moving forward in time. And you would think that, you flew off from your planet to a nearby black hole or star, and, everyone agrees that you left at 7 o'clock in the evening and you arrived at 7 a.m. the next day in time for breakfast. And then you turn around and you fly back to your planet. And in this picture of time that we have, everyone agrees on the time at which these events happened, right? There's like some big clock in the sky that everyone agrees on. But the reality is there is no such big clock on the sky, right? To measure the sequence of these events, you need to be the person at each one of them. You need to be the person traveling in the rocket or sitting on the planet or sitting at the black hole. And what you see on your watch will differ depending on where you are and which of these events you're at and how you're traveling through the space and the time. And that is, as I say, very counterintuitive, but it is really how our universe works. The second thing that you need to know, and this is, again, it's probably deep in you because it's one of the first things you learn when you're at school. Like I think really the first science lesson you have to learn forces and you learn magnetism and you learn gravity. So you say, name a force and you say gravity, but that's wrong. Okay, we shouldn't actually teach children this. I actually think we should just teach them space-time curvature directly, but I'm apparently a minority view here. Yeah, we teach them it's a force, which is okay, works on the surface of the Earth. What is a force? So the idea of a force is that it's something that changes your speed or direction. So in this picture particularly, I'm thinking about a change of direction. So I'm flying my spaceship past a planet, and it gets somehow pulled off course by this gravitational force. And, we think of this as being like, a kind of like a big magnet that sort of attracts the spaceship towards the Earth. But what I want to tell you is that that's not what's really happening. So in fact, we would say actually that there is no change of direction. So the picture that we should have is something like this, that it's not a force that's pulling us off course, it's space-time curvature. So I have it up on this slide, but Hassan told me, you have to do a demo. And I said, there's a reason why I'm in the mathematics department and not in the engineering department anymore. But okay, so he's responsible for anything that would happen. But okay, so the idea is this. Oh, let me start with a small one. So the idea is basically that you have to imagine that this two-dimensional surface, this sheet here, is space-time. So that's the first thing that's quite tricky in these pictures. So people always show this kind of picture when they explain space-time. But this sheet has two dimensions. I can describe it by two coordinates, but it's supposed to represent space-time, this unified space and time thing that I was talking about. And so it should really be four-dimensional. So already something three-dimensional, like a ball, is, okay, you can imagine that, but four-dimensional, maybe not, right? It's okay, right? You don't have to imagine four-dimensional space-time. I actually challenge anyone who says that they can imagine four-dimensional space-time. I don't think they can. But it's okay. As I say, it's just kind of schematic, so just take it as being schematic. So if this is my rocket, this marble. If I roll it across space-time, because it's quite light, it's quite small, it doesn't curve space-time very much. And so it just travels in a straight line. So this is like in a space where I'm traveling through empty space, right? And I just always move in a straight line. But what if I then put a star in the center of my space-time? Oh, that's not enough. I have to do a bigger star. Here's a bigger star. Okay, now my space-time has been curved. So the nice thing about this picture is it tells you where does this curvature, this space-time curvature, come from. It comes from energy and matter. So things like stars or planets curve the space-time around them. And so then when I come in with my little rocket, what I can do if I try and go in a straight line, I get deflected, right? I get pushed off course. And so we might describe this as being a force that's pulling this marble towards the star. But you can see that's not really what's happening, right? So actually what it's doing is it's following the contours of the surface. And because it's a curved surface, those contours are not straight lines, right? They are curved. So there's no magnet in this ball pulling this ball towards it. It's really just following the curvature of my space-time. So if I do it nicely, I'm not very good at this. if I do it like this, I can actually get it to go round in an orbit. And so this is actually what's happening with the Earth around the sun and the planets around the sun. Okay, we don't in-spiral so fast, don't worry. It takes a very long time for us to in-spiral towards the sun, and so we're all good. But yeah, so this is the concept of space-time curvature. And this is going to be fundamental to all of the objects that I'm talking about. So I'm going to show you lots of these two-dimensional pictures, which you have to remember are kind of schematic representations of four-dimensional space-time. So okay, I don't need my next two slides because I did it for you. Okay, but I have another picture that I really like to show. This is the one that I really like when I imagine space-time. And the reason is that actually most of the curvature is in the time direction. It's actually not in the space direction. So to quite a good approximation, it's time that's curved and not space. Okay, I said they were part of the same thing, so it's a bit subtle, but let me explain with my picture. So here are Sam and Liebert. These are my two PhD students from Queen Mary University. And so I decide, let's pretend that we live a long time ago, okay, where we don't know if the surface of the Earth is flat or curved. And I decide to send my two PhD students to Africa to do an experiment that I can't be bothered to do myself. That's what you do with PhD students. And so I send them to Africa and I tell them, okay, we're going to do an experiment. You need to start at the equator and you're going to line yourselves up so you're going parallel, right? So one here. And I tell them you're going to walk in a straight line, right? You're going to just fix your eyes on the horizon and you're going to head north. Right, you're just going to walk always in a straight line. Doesn't matter if you're being chased by lions. You have to walk in a straight line. Okay, so off they go. And if the Earth was really flat, then this picture is what would happen, right? They would stay separated. They would stay a certain distance apart as they traveled north. And when they got to Europe, they would find that they were still the same distance apart. But of course, I hope you know that our Earth is in fact a ball, and therefore that's not what would happen. If they both kept going north, eventually they would find that they were getting closer together. They would actually find that when they got to the North Pole, they would actually meet there, right? They would find that they'd been they got together at the North Pole. And so they might sort of be kind of confused about that if they thought that the Earth was really flat. So the reason that we thought for a long time in the history of people that these pictures were the same is because we live on this very tiny patch of the planet, right? So in a very small box, these two pictures look the same. People stay the same distance apart. It's only when you start to travel on distances that are similar to this curvature scale of the surface of the Earth that you start to see differences that tell you that it's a curved surface. So, okay, here's a more schematic picture of what I just told you. You've got north in space, and Sam and Liebert are going north. And in the left-hand picture, this is flat Earth, and in the right-hand picture is what would happen on the actual curved Earth. And if they were really determined, to hang on to this picture of a flat Earth, what they might say is, well, maybe there was some kind of mysterious force that pulled us off course. So we didn't go in a straight line, we got somehow pulled off course, and that's why we met at the North Pole. So that would be wrong, but they could, PhD students, what can you do? They might reasonably conclude that. And in effect, they could probably build a model where these two things look the same. So what I'm sort of getting at indirectly eventually is that this is exactly what's happening with space-time and gravity. So this mysterious attractive force, we call that gravity, but actually it's the fact that we're moving now through time, and time is curved. So instead of going north, I've replaced this north axis with time. So that's, as I say, that's quite a hard concept to think of, time being curved. But that is indeed what happens. And so you might ask me at this point, okay, Katy, this is all very interesting, space-time curvature, but to be honest, I've got to this point in my life, and I've never needed the concept of space-time curvature. Like, just thinking of gravity as a force has worked okay, and, frankly, what's wrong with just thinking of it as a force if in fact they're just equivalent? But the problem is that in some situations they're not equivalent. In some situations they're different. And in particular, in some situations you just can't describe what you're seeing with gravity being a force. So a really good example of this is that the universe is expanding. So this is called the Hubble expansion. Perhaps you've heard of it. But what happens is that if you take two galaxies, so these two galaxies are something like a megaparsec apart. So maybe you don't know a megaparsec, but it's a really long distance. So this is such a long distance that their individual curvatures, so if I come back to here, so the fact that they're individually curving the space, they're not affecting each other. So they're not being pulled together anymore by the sort of what we would call the gravitational attraction force, but that is really down to the curvature around each of these galaxies. So they're really very far apart. And what you'd find if you looked at these galaxies is if they started a megaparsec apart, 1 second later, they would be 1 megaparsec plus 70 kilometers apart. So they're actually moving away from each other. So that's really weird, actually. It's really hard to explain. Like, how do you explain that using a gravitational force? These objects are normal galaxies. They have positive mass and matter in them. And so they should, if anything, attract each other. Or, if they're so far apart, they should just kind of stay where they are. They should just stay a certain distance apart in time. But what Hubble showed is that, in fact, they are moving apart in this way. And the reason that they're moving apart is because the universe is curved in the time direction. So we never say this. We always say the universe is expanding. I would like people to say the universe is curved in the time direction, but it's not really caught on. So the point is that if you see it in this way, suddenly things make a bit more sense. So the interesting thing, which you'll notice immediately, is somehow the universe as a whole is curved in the opposite way to how it's curved kind of locally around objects. So this is completely consistent with Einstein's theory. It can happen this way. But the universe is somehow curved such that, it's like it being curved up instead of down. So instead of things sort of moving together, they move apart over time. But it's still curvature in the time direction. But as I say, if you think of it in this way, it's really nice, because a lot of the questions that people often have about cosmology and about the universe, you start to think of them in what I think is kind of more the right way. You start to ask the right kind of questions. So for example, one question that people always ask is, what is the universe expanding into? If the universe is expanding, what is it expanding into? But this is like asking, what's the Earth's surface expanding into? Or, would you describe the Earth's surface as somehow expanding as you move north? I mean, you kind of could describe it in this way, somehow the Earth kind of gets bigger as you get north, but it's not really expanding. It's like it's already there and we're just moving on this curved surface. So this is, in a way, how you should think about our universe, that it's just this kind of curved surface. So a more interesting question is to ask something about, can I go round the universe, right? Like I can go round the Earth. Can I sort of fly to the outer edges of the universe and go back on myself and come round again? Then another question that people always ask is, what came before the start of time? And this is like asking, what is further south than the South Pole, right? So if I rewind time in my picture of the sort of curved Earth, that's equivalent to saying, what happens when you get back to the South Pole? And you know that on the Earth, all people would come to the South Pole. There'd be nowhere else for them to go, right? You can't go any further south than the South Pole. So of course you can start asking questions about, well, somehow then you need to go off the surface of the Earth, right? You need to go into a higher dimension. So then, that makes string theorists very happy. They think about higher dimensions and things like that. But, maybe that's the right question to be asking, right? Did this come from some higher dimension? The two-dimensional surface of the Earth is somehow embedded in this sort of three-dimensional space. Okay, so let me get on to black holes, wormholes, and warp drives. So starting with black holes, so I think the really interesting question to ask yourself, so I hope actually everyone knows what a black hole is. I kind of assume that if people sign up to talks like this, they've at least watched one science fiction film where there's a black hole in it. But maybe I shouldn't assume knowledge. Sorry, Star Trek. If as long as people have watched Star Trek, you're definitely okay. You're going to really enjoy the end of the talk. So black holes, how do I make a black hole? So yeah, a black hole, as I say, the sort of definition of a black hole is a region of space and time that's somehow separated from the rest of the universe. So the idea is that you can't get out of a black hole. So there's some surface that once you've crossed it, you would need to travel faster than the speed of light to escape from it, and therefore, since, as far as we know, nothing can travel faster than the speed of light, everything gets trapped in a black hole. But the interesting question that I want to ask today is, how do I make a black hole? Because that's really a question about, can one of these things really exist? How real is it? And so, I can now use again my little demonstration. What I want to do is I want to make this deeper, right? So if I want things to get trapped in it, somehow I want this to make it go down. So I can put my heavier object, and you see it's getting deeper, right? So it becomes more difficult for something to escape. This is why I said I shouldn't be trusted with a demonstration. It's really quite addictive. So they said that they will leave it outside once we've finished the lecture, and everyone can play with it. And I tell you, it is massively addictive. But I need something more, right? So here we go. What have I got here? Oh! They said two hands. Bend your knees. Okay, so what I'm doing, right? What I'm doing is putting more and more stuff into one place. So it's not enough. So if you think about it, it's not enough just to make the ball bigger. So obviously making it bigger isn't going to sort of give me this kind of tube that I'm really looking for. I need to somehow contract this stuff into a small space. So I need something that's very dense. So this ball is very dense. So having a ball of the same size but a lower weight wouldn't work, right? So this is the thing we have to do. So actually what we have to do is we have to get all the mass that's in the sun, so all the matter that makes up our sun, and we have to sort of squash it into a region that's only 1 kilometer across, right? So 1 kilometer is like, I don't know, here to Green Park Station. Maybe it's not, maybe it's a bit further. No, okay, I've got no sense of distance. So what I need to do is sort of compact the sun into a region that's very small. And so on the face of it, initially, people thought black holes sounded crazy because they said, well, how did that happen? That seems like it would be really hard to do, right? Like, how do you get the sun and squash it? So initially, people thought that black holes were just a mathematical curiosity. So as I said, the point I wanted to make, I was going to do it with slides as well, but then they made me do it with this. So what I wanted to say is that actually, technically speaking, black holes are this event horizon. So it's quite interesting. We don't actually describe black holes by what they're made of. So if you think all the other things that we have in astrophysics, like a star or a planet, we generally describe them by what they're made of. But with black holes, we actually don't do that. We actually define them as just being this surface beyond which nothing can escape. And one of the reasons that we do this is because we really can't know what's in them. So there's actually no way, if I fly up to a black hole, for me to tell what it's made of. So was it made of stars? Was it made of bowling balls? Was it made of televisions that got thrown in? Whatever I throw into a black hole and make this black hole, once it's formed this event horizon, somehow I can't tell anymore what it's made of. So it doesn't really make sense to define a black hole as what it's made of. But you might really want to know, what is this object? So there has to be something in there, right? Like there has to have been something that fell in that curved the space-time that causes the black hole, the space-time to be so curved. And so we would really like to know, what is this object that's curving the black hole? So at this point, usually people naively, people sort of think, well, couldn't you somehow, fly into the black hole and then, look at what's in the black hole and then, but then no, you can't, right? So there's actually so many reasons that flying into a black hole is a bad idea. It's actually, always when I give this talk, at schools and stuff, all children want to fly into black holes. They're like, I could fly into the black hole. Like, no, don't fly into black holes. Like, fortunately, they don't have any way to do it, so it's okay. But I'm always telling them, like, no. So obviously, firstly, once you go in, you can't get out again. So it's pointless, right? Like, even if you went in and you looked and you found that the black hole was made of stars, you couldn't go out again and tell anyone, right? So somehow that knowledge is trapped in the black hole with you. Then in addition, it's deadly to fly into a black hole. So at some point, because it's very curved, so it's actually quite nice in this picture, the part of you that's closer to the black hole will be kind of falling into the black hole much faster than the part further away. So somehow, the gravitational force on is different on the part of you that's closer to the black hole and further away from the black hole. And so it ends up stretching you. And this tidal stretching force will actually kill you at some point. So it doesn't actually necessarily happen as you cross the event horizon. A lot of people think it's like a property of the event horizon. So some very supermassive black holes, you could still cross the horizon without being torn apart by tidal forces. But eventually, as you got closer and closer to the center of the black hole, you would die. So it's as I say, it's really not a good idea. And the final reason why it's really not a good idea to fly into a black hole, or even very close to one, is this point about time that I mentioned earlier, that time changes. So if you go very close to a black hole, and then you fly back to your planet, what you'll find is that time hasn't passed as much for you as it has for everyone else on your planet who is a long way from the black hole. And so actually, when you get back home, it's a bit sad. Everyone you ever knew is gone, and maybe, I don't know, your planet's not even there, it's been taken over by aliens. So as I say, don't fly into a black hole. Not a good idea. But of course, black holes do exist. I've told you they do exist in nature. So how do they form? How are they made? How do we crush something the size of the sun into something a kilometer across? Well, it turns out that actually nature does it for us. So this was first realized by Chandrasekhar. So Chandrasekhar actually gave a talk just down the road from here at the Royal Astronomical Society, roughly 100 years ago. And he gave this really fantastic and interesting talk on some research he'd been doing about massive stars. So what he'd realized is that if you have a very massive star, when it comes to the end of its life and it's burnt all of its fuel, it will start to collapse. And people had said, well, even though it starts to collapse, at some point it will be supported again by electrons in the matter of the star moving around very fast. But what Chandrasekhar realized is that's actually at some point not enough. So the electrons would start to have to move faster than the speed of light to be able to support the star against further collapse. And since we know that things can't move faster than the speed of light, he concluded that therefore it must continue to collapse. And actually this would end up creating something that was compact enough to form a black hole. And so he said a star of large mass cannot pass into the white dwarf stage, and one is left speculating about other possibilities. So he realized this was quite controversial, and so he put it in this slightly, polite way, speculating about other possibilities, but he understood what he was saying. So unfortunately for Chandrasekhar, the next person to take the stage was Arthur Eddington. And Eddington was an expert in general relativity. So actually, Eddington was the person who proved that Einstein was correct about general relativity by measuring the bending of light around the sun. But he really didn't like this idea. He said, I think there should be a law of nature to stop a star behaving in this absurd way. But notice the language he uses, right? I think there should be a law, but there isn't one, right? So he was actually wrong, and it was just his idea that this should not happen, that this was a crazy idea, this couldn't possibly be true, that led him to completely discount the perfectly valid scientific result that had been presented to him by Chandrasekhar. And it was really unfortunate because actually, of course, Chandrasekhar was right, but because Eddington was so well known and influential and considered so clever, everyone listened to him. And so the whole scientific community just rejected this idea that Chandrasekhar had. And it was 40 years later, 40 years, before this idea was kind of revived and shown to be correct. So it was a kind of a big setback for science. And of course, you can actually speculate a bit about the fact that Chandrasekhar, being an Indian, was there an element of racism in this dismissal of his idea? I think that's certainly a possibility, and it was certainly something that he felt was the case, which is why he left the UK and went to the US. But it was definitely a prejudice against how we think that our universe should work, right? We have these very strong prejudices about this is how our universe is and it can't behave another way. And this led, as I say, to this idea being sadly discounted. So even with this idea about stars having to collapse inevitably into black holes at the end of their life, the real proof that a black hole is not a crazy idea is experiment, right? Is observation. Like ultimately, the real test is, do we see them? Do they exist in our universe? And so, yes. So there's been some really exciting developments recently in black hole observations. So this is one of them. There's actually been a photo taken of the black hole at the center of our galaxy. This is the photo. And so this is completely consistent with what we expect a black hole to look like. So obviously we're not really seeing the black hole. So in a way it's a bit of a cheat to say it's a picture of a black hole. We're really seeing the sort of hot gas and dust around the black hole that's falling into the black hole. But what we see is that there's this dark patch at the center, right? So this dark patch is a part where there is gas and dust falling in, but somehow the light from it can't escape anymore because it's gone past the event horizon. So this image is, in a sense, the most direct proof we have that black holes exist. So unfortunately for the people at the Event Horizon Telescope who made this very nice image, which was obviously a very massive scientific achievement, Hollywood made one before, and actually only a few years before. So I felt really sorry for the people at the Event Horizon Telescope because when they unveiled their image, I think everyone was expecting this, and then it was like, it was this. So there was a bit of like, oh, that's nice, But, okay, you can't beat Hollywood, right? But, this is a Hollywood image. So it's from the movie Interstellar. Has anyone seen the movie Interstellar? Yeah, of course. So someone said, of course. I take nothing for granted. So this is the supermassive black hole that appears in the movie Interstellar. And it was really impressive because they actually did a scientifically accurate representation of what the black hole would look like. So this maybe, I don't know if you can see the reference, but it's from a journal, Classical and Quantum Gravity. So it was actually published as a scientific result because no one had done such accurate simulations of what this would look like before. And it looks kind of fantastic. And indeed, it kind of matches what we actually see. So the second really exciting advance in black holes, in observations of black holes, is this one, is gravitational waves from black holes. So this was in 2015. We had the first observation of gravitational waves coming from binary black holes. So it turns out that black holes can exist in pairs, in binaries, where they orbit each other over time. And because they're emitting these gravitational waves, they lose energy. So very much like my ball going around here, eventually it will spiral in and they will merge. And so when they merge, it's a hugely energetic event. And there is this ripples in space and time, these gravitational waves that are given off, and they reach us here on the Earth, and we were able to measure them in 2015. So this is the image of the wave that was seen. So this, this is the signal that was detected. And so for me, this is quite a kind of personally exciting image. So 2015, so I actually started my PhD in 2013. So I was 2 years into my PhD when this discovery was made. And my sort of job, my day job, certainly during my PhD, was to generate these signals, to do computer simulations that predicted what these signals would look like. And so I was spending all day generating signals like this, and then suddenly, wow, here they were in reality. And we all got called into the seminar room, and we were sitting and watching the broadcast, and it was just such a, it was quite emotional to see that this had really been detected on Earth. But as I say, yeah, this is the ultimate proof, right? So black holes are real science; they're not science fiction. And the reasons are that they don't violate any fundamental principles. In addition, they really are inevitably the endpoint of supermassive stars. And then, of course, finally, the proof is that they've been observed. Wormholes. Okay, maybe Dan can take away the... I can't make a wormhole demonstration. So this is why I said I can't do a demonstration, because how do you make a wormhole? Well, I guess we could. So I hope you all know what wormholes are. Again, if you've watched enough science fiction, you'll probably know. We had a Star Trek fan, right? Good. Yeah, so this is an image from Deep Space Nine, which is, in my view, one of the finest Star Trek series. But I have to say that, thanks, Dan, that I have to say that their picture of a wormhole, I'm not actually so keen on. It's not quite right. So you can see it looks like a tunnel. So as I say, again, I kind of assume people know what wormholes are. So wormholes are somehow like tunnels that take you from one part of the universe to another quickly, a shortcut that stops you having to go the long way round through space. So in Deep Space Nine, it takes you from the alpha quadrant to the delta quadrant. It's very useful. This one is sort of shown like this tunnel. It sort of opens up like, whoosh, and then you fly into the tunnel, and it's got like an entrance way. And certainly they were influenced by this picture of wormholes. So again, this is one of these two-dimensional pictures of four-dimensional space-time. So this is quite a bad picture because the rocket is like not on the surface. So in these two-dimensional pictures, you're supposed to stay on the surface, right? You can't go into the higher dimension. You're supposed to roll along the surface like a marble and then go through this tunnel and come out the other side. So this is the kind of two-dimensional picture of the four-dimensional wormhole in space and time. And fortunately for us, Interstellar made another picture that was much better of an intra-universe wormhole, so one that's going from one point to another. So this is the image they made. And again, it's scientifically accurate in some ways. So what a wormhole would look like is this. It would look like some kind of soap bubble. It doesn't have an entrance, right? Like you can fly around this bubble and you can go into it from any direction. And once you go in, you'll go through this tunnel and you'll come out the other side. Well, in principle, that's how it works. And what you're seeing through the wormhole, these things that make it look like shiny, that's the light from the galaxies and the stars on the other side of the wormhole coming through the wormhole to you. So this is how it would really look in space. Okay, so let's play the game like we play with a black hole. How do I make a wormhole? So this is when we start to immediately have problems. So I want a wormhole, but I want to be able to go through it. So a traversable wormhole is one, you might have noticed it kind of looks like two black holes stuck together. But I don't want it to be two black holes stuck together, because if it's two black holes stuck together, I'll get stuck once I get to their event horizon. So you can have it so that, if you went through the event horizon, you'd end up stuck in this. Let me go back to this image. You get stuck in the middle of this throat, and you couldn't go out either end. And that would obviously not be a useful wormhole. I want one that I can go all the way through. And I also don't want to be pulled apart by these tidal forces that you get when you get sort of into a black hole. So if I want those things, then I need exotic matter in order to support the wormhole. So what is exotic matter? So just broadly speaking, exotic matter is something that has negative energy. So you could ask, what's negative energy? That's a very good question. So everything that we know of in our universe has positive energy. So, you, me, stars, planets, everything is a positive energy object, right? So even things in cosmology that we don't understand very well, dark matter and dark energy, these components of our universe that we actually don't understand, they also have positive energy. And so they're not something that we can build a wormhole with. But okay, if we just assume that somehow we do get some negative energy from somewhere, then can I somehow stuff this negative energy density into one place and punch a hole through space-time and then have it form a wormhole? No, is the short answer. So it turns out that is just forbidden by the laws of physics as we know them. So the really difficult thing is this punching a hole. So if I want to go from the image on the left to the image on the right, I want to go from this sheet to this wormhole thing, what I need to do is fold it over, and that's okay. But then I need to somehow punch a hole, as I said, in the top and bottom, and then stick them back together. And it's this punching a hole and sticking back together that seems to not be possible. So forming a wormhole in this way, so building one from scratch, is somehow not allowed. However, if one already happened to exist in the universe, if, say, during the Big Bang, the universe formed with lots of connections between different points in space-time, then maybe I could get hold of one of these and reinforce it with some additional exotic matter and then use it to go through. So this is mining wormholes. So we want to mine wormholes, we don't want to build them from scratch. So Matt Visser compares this to a recipe for dragon stew. First find a dragon, right? It kind of seems, so it's not like black holes, right? So with black holes, we have a sort of a natural way for them to form in our universe, whereas with wormholes, we kind of have to say that they're already there. The thing that really sort of does it, I think, for wormholes is that they allow time travel. So has everyone seen Back to the Future? I don't know, because I showed this to one of my younger collaborators the other day, and they were like, what's Back to the Future? And I was like, no, this is not possible. You must know what Back to the Future is, right? Okay, anyway, so for young people who are, it's not on TikTok, so don't know. Back to the Future, Marty uses a flux capacitor, okay, it's not real science, uses a flux capacitor to go back in time and accidentally prevents his parents from getting together, thereby, stopping himself from existing. And so he has to fix it before he goes back home. So already you see, there are lots of problems, right? When you start to have time travel, we've all watched films with time travel in, and it's always a mess, and it's always unsatisfactory because somehow it doesn't all join up correctly. So really, this is what in physics we call this concept of causality, right? So causality is really at the sort of the base of every physical theory. And it's this idea that somehow, things have an ordering. And so, if I have a fire and that fire spreads over time, and then it sets some factory on fire, then there's an explosion at that factory. That explosion cannot have started the fire, right? So I can't have a loop in time, right? I can't have the thing that happens in the future causing the thing in the past. And this seems so obvious that it's we hardly ever say it. It's always like a, zeroth or minus one law of physics that there should be this idea of causality. And wormholes, as I say, wormholes potentially break that. So in order to make these closed time-like curves from wormholes, you have to take the two wormholes and you have to make them move relatively to each other. So the two mouths of the wormhole, you have to move them relative to each other, and then you have to kind of bring them together. And at some point when they get close enough, they will form one of these closed time-like curves, these loops in time, and allow you to travel backwards into the past. So obviously people really don't like this. Like, this is really bad. So there are some solutions. Saying that they're solutions is probably a bit strong. I don't think they've really solved the problem. They are all conjectures. So how could I have wormholes and still have things be okay for time travel? So most of these are from science fiction, so I don't really need to explain them. But there's multiple universe timelines, right? So when Marty goes backwards in time and he stops his parents getting together, the idea would be here that he doesn't affect his timeline. There's somehow a branching of a new universe that comes off in which his parents don't get together and he's never born. So he can still exist because he comes from this other timeline, but there are then multiple universes kind of branching off every time someone does one of these time-traveling events. And so the problem with this is, we have no known mechanism for branching the universe into many different time paths. That's, as I say, that's still science fiction, sadly. The Novikov consistency conjecture, this is a very sort of formal sounding name for something that, again, you probably know from science fiction films, so what happens here is, this is like where I go back in time to try and stop my friend being killed, but then somehow accidentally I become the person that kills her. So somehow what has happened must always happen. So despite the fact that I go back in time, I can't change things. History is set in stone. And by going back in time, I will only, propagate that loop as it has always been. And so this is very unsatisfactory for the same kind of reasons that the films that include it are very unsatisfactory, because it's somehow very contrived, right? It means that we don't have control over what we do, and it makes things that are very unlikely somehow certain. So I go back in time to try and kill someone, it means that the gun must jam at the last minute, which would be a very unlikely event, but somehow has to happen because I can't be allowed to kill this person. So this one, as I say, I find a bit unsatisfactory. There's also the chronology protection conjecture. So this one is if you think of the wormholes, I had to sort of bring them somehow together to form this closed time-like loop. And so this one sort of says something, sort of maybe quantum physics, quantum gravity, waving my hands here, something stops me from moving them close enough together to form this time-like loop. So somehow they will repel each other in a way that prevents me from ever forming this closed time-like loop. And of course, the final one, and probably sadly the most likely one, is the boring physics conjecture, which just tells you that wormholes sadly don't exist. Okay, warp drives. Warp drives. Warp drives, again, if you're a Star Trek fan, warp drives are everyday stuff. So the idea of the warp drive is actually very inspired by cosmology, by this idea of our universe expanding. So the space in front of my warp ship is contracting over time, and the space behind is expanding over time. And so this somehow drives me forward through space. So for me, I just feel like I'm kind of sitting there in this bubble. But for someone outside the bubble, I'm traveling potentially faster than the speed of light. So you don't have to travel faster than the speed of light in a warp ship. It could be one that traveled slower than the speed of light. But somehow you're being powered forward by this contraction and expansion of space-time behind and in front of the ship. So the bad news. Warp drives, like wormholes, require exotic matter. So we have all of the problems associated with needing to find some sort of negative energy material. They also violate causality. You can also create these kind of paradoxes where you generate time travel. And so again, they're slightly unlikable for that reason. A really practical point about warp drives is, how do you steer one? So it turns out that if you're in this bubble and you want to send a signal to the front of the bubble, you can't, right? You actually can't get a message to the front of the bubble, and that means you can't turn it off. So once you're in the warp drive, you just kind of have to keep going, right? So that's not, again, very useful if you really want to use it as a warp drive for traveling through space-time. But okay, let's just set these aside and see if we could make gravitational waves run. So this is, I have to emphasize, this is a bit of a hobby of mine. So I'm very aware that most of the people in the audience are probably British taxpayers, and you do pay my salary. So I want to assure you that I do actually do other more useful stuff in my main research. Well, you can judge that for yourself. I also do teaching. So in my spare time, my hobby is to simulate warp drives. So as I say, these objects, although they're science fiction, they actually have quite good descriptions in physics. And so I can actually build one in my computer simulation, and I can actually see whether I can generate gravitational waves from it that maybe could be observed here on Earth. So it's an international collaboration. Jim T. Dietrich is the captain. So he's actually an expert in neutron star physics from Potsdam University. I also have Sebastian Roth-of-Kahn, who is an expert in gravitational wave data science and data analysis from Cardiff University. And then there's me, and I'm very much like Scotty in the original Star Trek in that I do all the work. And these guys literally do nothing. So Tim just writes me emails saying, have you done the simulations yet? And I'm like, I have a day job, so I have to, there's things I have to do. And Sebastian just sends us all Star Trek memes all the time, and episodes of Star Trek that he's been watching, thinking about warp drives. So as I say, I am the one who does all the work. And so we've actually done some calculations. So this is to prove that we have calculations, we have simulations. We even wrote a code to do this. So this is our computer. It's available on GitHub. So for anyone who wants to download, it's publicly available, warp drive code. And I will now share with you our results. So in this slightly poor-looking movie, you can see that there's a blue patch and a red patch. And so the blue patch is the part of the space-time that's expanding behind the warp ship. And the red part is the part that's the part that's expanding, and the red part's the part that's contracting in front of the warp ship. So like in my previous picture. And so the premise for this simulation is the containment field for the warp drive has broken down. And so the warp bubble is going to collapse and give off gravitational waves. Okay, so are you ready? Are you watching the bubble? Okay. So the thing that took me the longest was actually attaching the soundtrack to this movie. Doing the simulation was easy, but then I couldn't work out how to do the thing. So I'll show it to you again because I'm so proud of it. I have to go back. Thank you. So what you might have seen is that it's actually very bad for the people in the warp bubble. So you probably noticed that everything kind of collapses inwards before it goes out again. So actually they would be completely torn apart by this stretching of space-time, and they would sadly, unfortunately die. But you can also see that there are waves being given off. So now we have these gravitational wave signals that we've generated. We can actually go and look in the data from the LIGO gravitational wave detector, and maybe in the future, you may see this news article saying that Einstein's gravitational waves have been seen from warp drives, or sadly, maybe not. Okay, so that's all I wanted to tell you about black holes, wormholes, and warp drives. I had this, what's the difference between a crazy idea and a brilliant one? So that was the premise of my talk. So when I started writing this talk, I actually thought it would be quite easy to say, no, this is where the line is drawn. Don't worry, guys, we've got it all under control. We know what's real and what's not real. But actually, some of the issues were quite subtle. These questions that I raised about exotic matter, there are cases where you have quantum effects, where you can generate small amounts of negative energy density, not enough to power a warp ship. But, in principle, there are aspects of physics that we don't understand well, particularly this quantum realm where you have very small scale physics that interacts with gravity. We just don't understand that well. So, sometimes, I can think, maybe somewhere in the universe, someone has figured this out, and they've figured it out in a way that they can use it to power warp drives, for example. I think, unfortunately, it's probably not the case. It's the boring physics conjecture is going to win out. But, we should always remember the story of Chandrasekhar and Eddington, and remember to keep an open mind to these kind of ideas. And so I will stop there, and with fear and trepidation, ask for questions.